All right, guys. So what we're going to be looking at today is limits of functions analytically. Now, what does that mean, first of all? So when we say analytic, what we mean basically is that we're going to be using algebra to evaluate limits. Using algebra to evaluate limits. Okay, and so there's a lot here actually. Now there's a few different problem types that we need to go over in detail, and specifically you're going to want to pay real attention, because if you have a problem that's one particular problem type, you can't really solve it with any other method other than what I'm going to do. There may be very slightly different algebra steps that you could take, but the basic idea is going to be the same no matter whether you're copying me or you're copying somebody else. Okay, so you're going to really want to say, oh, well, it's this type, so I should do it this way. All right. So anyway, let's go ahead and get started. So before we do much, what I want to do is just remind us of what we ought to be able to do now. So from previous sections looking at limits, maybe we ought to know this. If not, then you're learning it now. So some limit stuff that we know. Okay, so basically these are just going to be some rules that we're going to follow. Rules. Okay, if you have a limit as x goes to some number of a constant, and that constant k is a different number, then that is just going to be k. Oops, I'm on the eraser still. Have to remember how to use this. Okay, so that's going to be k. Now, what does that mean? As an example, like if you have the limit as x goes to 3 of 17, the answer there is just 17, right? Because x may be going to 3, but the 17 isn't an x, right? So x goes to 3, but there are no x's. So when you take the limit as x goes to 3 of 17, you just get 17. Okay? And what else can we do? Well, we should also know how to find the limit as x goes to a of x, right? That's just going to be a. And as an example, limit as x goes to 3 of x, what's that? 3. Right? So this is different than the previous one because x goes to 3 and this is an x. So x goes to 3. And what else do we know? We learned a few other rules. I guess I should write them. So like if you have x goes to a of x to the n, that's just a to the n. What's that look like? Example is x goes to, let's do a 2 this time just because, of x to the 3. What would you do? Well, basically you just take this 2 and you replace the x with the 2. And you would get 2 to the 3 and you would get 8. Okay? Now, what else can we do? I think a few more. Just to summarize here, x goes to a of a constant times f of x, like that. You would be able to take that k out of the limit, like so. What does that look like? Example. So like if you have a limit as x goes to 3 of, what do I want? How about 5x squared, right? The way you would evaluate that is you would say, okay, well, applying this rule, the 5 should just be able to move out in front. So if you do that, you get 5 limit x to 3 of x squared. And of course, you already know how to evaluate limit as x goes to 3 of x squared. You just put in the 3, so it's 5 times 3 squared, which is 5 times 9, which is 45, and then that would be your answer. Okay, so that's just how to do some really basic limits. We can also, hopefully we learned this as well. If you have a limit as x goes to a of a function and another function added or subtracted, then you can just do those separately, two separate limits. Where would you use that rule? You would use that rule on something like this, where you have a limit that's like x goes to 2 of like x squared plus x cubed. Now you don't have to formally apply the rule, right? I could write it this way: x to 2 x squared plus the limit as x goes to 2. Oh, I said x cubed, but I wrote 3 cubed. Okay, x squared plus x cubed. Like that. So you could write it as two separate limits, and then each of the limits you evaluate separately, so you have to plug the 2 into the x, and then you separately have to plug the x equals 2 into that x. And so you're going to get 2 to the 2 plus 2 to the 3, which is 4 plus 8, which is 12. Okay? But normally what you're going to do is you're not going to write this. You're just going to go from here to here. Right? That's just a lot easier. Just put the 2 in for both of the x's. Okay? That's the way you'll apply that one. And I believe we also had the rules for multiplication and division as well, right? Limit as x to a of f over g is a limit as x goes to a of f over the limit as x goes to a of g. And last one, limit as x goes to a of f times g is again limit as x goes to a of f, limit as x goes to a of g. Right? And I'm not going to write out examples of those. We're just going to see them anyway as we go. And so you're supposed to already know these rules. Now, what I want you to do, though, is think about these, right? What these are basically telling you is that when you combine all of these rules, is that when you see a polynomial, it's pretty easy to evaluate. So when you see a polynomial in a limit, it's pretty easy. I'm just going to say easy because I don't want to have to write pretty easy. So like if I say limit as x goes to 2, and then I have, I don't know, like 3x plus x squared minus 5, right? You could formally apply all the rules, but what you really want to do is just take this 2, because x is going to 2, and replace all of the x's with 2. And you would just get 3 times 2 plus 2 to the 2 minus 5. And you work that out and you get what you get. So 6 plus 4 minus 5. So it's 10 minus 5, which is 5. Right? And that's what you do. Okay? Now, if that's all you do, then why do we have 2 more homework assignments on evaluating limits this way? And the reason we do is because there are going to be some limits that you can't just plug in the numbers because you're going to get something that's undefined. Okay, so let's see, what does that look like, right? But, nope, right here. But some limits are undefined, or I shouldn't say that, I'm erasing that. are not directly, nope, try again. Some limits are, what are they? You can't evaluate them just the way they're written. For some limits, you can't evaluate them the way they are written at first. Okay, now what can go wrong with them? Well, mostly you're going to see a lot of divide by zeros. Okay. A lot of divide by zeros here. Right? And you know that divide by zero means, or dividing by zero is not a defined operation in math, right? That's not allowed. Not allowed. Okay? So I'm not really ready to get into the types of limits, like all of them that this is going to occur in, but here's just a couple of the ones that you can't just evaluate the way that they're written. Examples. We're not going to solve these right now. But like if I say limit as x goes to 2, and then I go like, what do I want? X squared minus 4 over x minus 2. Right? You wouldn't be able to evaluate that limit just by plugging in the x equals 2. Because if you plug in the 2 right there, and you plug in the 2 right there, and you think about what happens, what does happen? Well, try it. Try to plug in the 2. You get 2 to the 2 minus 4 over 2 minus 2, which on the top is 0, and on the bottom is 0. And what does that mean? Right? I'll tell you what it doesn't mean. It doesn't mean that there isn't an answer. What it means is that you have to do more work, right? So when you see this, this means do more work. You're not done. Okay? And that's the kind of thing that you're going to see. You're going to see it like that. You're going to see it in other contexts. Like you'll see it like this. Forgot a limit. Limit x to 5 maybe. X minus 5 over 1 over x minus 1 over 5. Like that. It's really the same kind of issue, right? Because if you try to plug in the x equals 5 here and here, you're going to get 5 minus 5 over 1 over 5 minus 1 over 5. And of course, that's 0 over 0 again, which means we have more work to do, right? You're not done. It means we're starting the problem. We're not finishing the problem. Okay? And so all of those divide by zeros are going to be problems for us that we have to understand and be able to figure out. Okay? Now, the first one that we're going to deal with, though, is going to be not the ones that I just wrote down, actually. I want to do them in kind of the order that you're going to see them in the homework. So in homework 4, you're going to see this. So in homework 4, you'll see this kind. What kind? Like this. The first kind that you're going to see is going to be like this. Limit as x goes to 2 of, and maybe they'll go like this, like x minus 2 up on top, and then maybe they'll go x minus 2 on the bottom. Okay, and so what makes this different than the ones that I just showed you is the absolute values, right? The absolute values are tricky to deal with. Okay, and so this problem is actually going to have the most kind of explanation involved in terms of theory, like what's going on here. A lot of these others, like the kind that I wrote up here, they just need algebra tricks. And once you know the algebra trick, you know everything that you need to know. But this one with the absolute value, like I said, it's a little bit harder to get a handle on. And so I will show you what's going on. So I know in the previous section that we evaluated limits with, what's it called? We evaluated limits using tables and things like that. And so let's think about doing that limit right there with a table. Oops, not that. Let's try to figure out what's going on here. And so if we're taking the limit as x goes to 2, I know that I need values close to 2 that are either greater than 2 or less than 2. And so let's go ahead and make a little table of values here. So if I say x minus 2, x minus 2, and we're not going to plug in a lot of values, but we'll plug in a few. So let's plug in a few values to the right of 2. So values to the right of 2 are like 2.1. That's a little bit bigger than 2. 2.01, 2.001. And then values to the left of 2 are like 1.9 maybe. And I don't think we need to do 3, so I'm just going to do one more. And 1.99. Right? So I got 2 to the right, or 3 to the right and 2 to the left. And now what we need to do is we need to calculate this thing for all of those x values. Okay, so you get out a calculator and you calculate them. So let's do the first one. So for the first one, you're going to plug in 2.1 into that fraction. So you're going to get absolute value 2.1 minus 2 over 2.1 minus 2. Well, what happens? On the top, you do the subtraction, you get absolute value 0.1 over 0.1. But the absolute value of 0.1 is 0.1. So you get just 0.1 over 0.1, which is 1. So this is 1. Now, if you put that in, put what in? If you put in the x equals 2.01, pretty much the same thing's going to happen. So if you go x equals 2.01, what you're going to get is absolute value 2.001. I don't know why I put an extra O. 2.01 minus 2, writing's hard, over 2.01 minus 2. And same thing happens, you get, after you evaluate the absolute value, 0.01 over 0.01. What's that? Still 1. So this one is also 1. So the first one's 1, the second one's 1, the third one, spoiler, is 1. So all of them to the right are 1. Now what about to the left though? Let's try this one, the 1.9. If you try to put in x equals 1.9 into this fraction and see what happens, you're going to get 1.9 minus 2 in absolute values over 1.9 minus 2 not in absolute value. So you get absolute value negative 0.1 on top, right? 1.9 minus 2. On the bottom, you get 1.9 minus 2, which is minus 0.1. Then on top, you take the absolute value. The absolute value of negative 0.1 is positive 0.1. So you get positive 0.1 over negative 0.1, which is negative 1. Not positive 1 this time. So up on your table, this is a minus 1. And I'm not going to do the last one, but it's also going to be a minus 1 for the same reason. So what happened here? So what happened here is this. If you look at a graph of this function, y equals absolute value x minus 2 over x minus 2, you get something like this. So you have a set of axes. You've got x equals 2 somewhere. So let's just say 1, 2. There's 2. And then put 1 up there, minus 1 down there. So what happens is when you're to the right of x equals 2, so to the right, then all of your y values are 1. So the right-hand half of that graph looks like that. Now on the other side, to the left side of 2, then you're at negative 1. That means looks like this. That's your graph of your function. And so when you do the limit from the right on your graph, which remember we did these graphically last time, the limit from the right is up here, up at positive 1, and the limit from the left is down here, down at negative 1. And so what's the limit overall? Well, on one side it's 1, on the other side is negative 1. You don't get the same answer both times, and so that means that the limit does not exist. So it's a lot of scribbling, but what's the punchline here? So here's our answer. The limit as x goes to 2, x minus 2 over x minus 2 is, well, it's nothing. It does not exist. Right? Because it's this graph right here. Now, if you want to save yourself a little bit of time, or not time, but maybe you should, you can at least, go to a website and graph that function and see how it goes. So, so you could go here and we could try maybe Desmos is a good site. All right, here we go. So like if I go absolute value, x minus 2 divide x minus 2. All right, there you go. I'm going to make the graph a little nicer. Projector mode. Okay. Well, there you go. So that's just the graph that we just saw. And so what's the limit as x goes to 2? Again, there's on the top, you come from the right and you end up at 2. On the bottom, you come from the left and you end up at negative 1. So, sorry, I said 2, but top, the y value is negative 2. Bottom, the y value is... I can't talk today. On the top, as x goes to 2, the y value stays 1. On the bottom, as x goes to 2, the y value stays negative 1. And they're not the same, and so the limit does not exist. Okay? Now, as soon as you can do that, they're going to try to trick you. Okay? If I have another problem like this, let's say I have almost the same problem. Let's say I want the limit as x goes to 3 of absolute value x minus 2 over x minus 2. Well, this time it's a completely different question. The answer here is actually going to be 1. Why? Well, x goes to 3, right? Where's x equals 3 on this graph? It would be like right here, right? That's where 3 would be. So if you were trying to evaluate this limit graphically here, you trace the curve from the right, you get there. You trace the curve from the left, you get there. And so this point right here, that's going to be the point where your limit is at. And so you just would need to know what is the y value there. And the answer is 1. Or, without the graph, you could just take this 3 and plug in the 3. And you would get absolute value 3 minus 2 over 3 minus 2, which is 1 over 1, which is 1. Okay? Now, why am I allowed to just plug in the x equals 3 there? Okay? And there's a theorem which they don't actually give you right away, but it's important to know. There's a theorem which says if f of x is continuous. This is actually not really a theorem. This is actually the definition of continuous, but I'm saying it's a theorem here. If f of x is continuous, then the limit as x to a of f of x equals f of a. We'll talk a lot more about continuity later on. But what it says, if the function is continuous, you can go ahead and just plug the a into the x, right? Which is what we just did right there. So what does that mean for doing these problems? What it means is this: from a practical standpoint, so generally here, to evaluate a limit as x goes to a, try to plug in a. Try to plug in x equals a. If your function is fine with that because it's continuous at a, which means like no holes or anything going wrong there, then if you get a number, basically that's going to be your number. If the function is nice, which means continuous here, if the function is nice, then the number you get, your answer is the limit. Right? And that's what we did. That's what we did right here. And that's not what we did here, because you can't just plug in a 2, right? We tried to plug in 2 here, and we got 0 over 0. So that's bad. Same thing here, right? Like on these, you can't just plug in 2 because you get 0 over 0. Here, you can't plug in x equals 5. You get 0 over 0. Here, you can't plug in x equals 2. You get 0 over 0. And so on, right? So that's the kind of thing that stopped you from being able to just plug in a number, right? So when you have absolute values, basically it's like one of these two examples here. Either you kind of need to think about it in terms of a table where you evaluate from the left and from the right, or if they're being sneaky, then the number that you're taking the limit as x approaches is not going to be the one that causes zeros. And if it doesn't, then you can just plug it in. Okay? And that's because of that theorem. So that's how you're going to deal with those absolute value ones. And if you get confused, you can always fall back on going to a computer and plotting the function so you can see what happens. And you would be able to see here, like at 3, there was no problems, right? what do you get at 3 from the left and from the right? You just get 1. But at 2, that's where the problem is, because that's where the function jumps. All right, enough of that. Let's go back to what we were doing. So that's how you're going to deal with those. All right. Now that we've done that, then I want to talk about 3 other types that you're going to see. Okay. So here are the 3 types that you need to know how to evaluate. 3 types. Now, some of them are in homework 4 and some of them are in homework 5. So either or. There are 3 types of limits you need to know how to do the algebra for. All right, and they don't really have names, but I mean you can summarize them in a way that makes sense. So here's one type. So one type I call the polynomial type. Okay, now here's what it looks like. This is just going to be an example one. So let me think. The minus 3 plus 4. What's that? X. Minus 3 plus 4. 12. Okay. Something like that. All right. Now, how are you going to recognize it? What you want to recognize is that it has a 0 over 0 when you try to plug in the x equals 3. So when you try to plug in the number, all right, and it's a polynomial on top and bottom. So that's how you're going to recognize it. Okay. I don't know why I was writing in red. Switching back. So that's a polynomial type. Another type you're going to see is going to be what I call the square root type. And you do this in homework 4. So let's see, square root type. Okay. Here's an example of one. So top is going to be 0 if you plug in a 5. And then on the bottom, I need something else that comes up 0 and just has a square root in it somewhere. So lots of ways I could do this. Here's one way. I think I did it. All right. So how does this work out? Well, think about, it's pretty much the same idea as the last one, right? If you try to plug in x equals 5 here, the top is going to be 0. And if you try to plug in a 5 in the denominator here, you're going to get square root 5 minus 4, which is square root of 1, which is 1. And then 1 minus 1 is 1. So it's still 0 over 0. And has a square root. Right? So, the names are not mysterious. These are just made up names, right? So I call it a polynomial type if it's polynomials, call it a square root type if it's got square roots, and we'll call it something else if it's got fractions. What do you think we'll call it if it has fractions? I'm just going to call it the fraction type. Okay. What's it look like? Again, there's a lot of variety in these. But, something like this. and it's going to be the same deal. You can't just plug in x equals 3 because you're going to get 0 over 0, and it has fractions. You get 0 over 0 again, and it has fractions. Okay, and so those are the basic types, and they all have separate algebra techniques that you need to know, right? That's kind of the key, is knowing that, okay? So each type has its own like algebra way to solve it. Okay, and that's what we need to know. So let us figure it out. So which one should we start with? Guess it doesn't matter. Polynomial type's easiest. Let's start with that one. I lied. Square root type shows up first, so let's do square root type. All right, so let's try it. Square root type. I know these are in homework 4. All right, so what is the deal here? So the deal with these is that you need to do what they call multiplying by the conjugate. By the way, this is probably the hardest type to solve this way, so, you know, keep that in mind, that if this looks hard, it's probably harder than what comes next. So square root type. So the algebra you need is multiplying by the conjugate. Okay, that's what you need. Now, what is multiplying by the conjugate? So conjugates are anything that's a minus b and a plus b. So any a minus b and a plus b are conjugates. Right? So the only difference between them is the sign, right? So this is a minus and this is a plus. Otherwise, they're identical. Anything that matches that pattern is called a conjugate pair. So these are conjugates. Now, what's special about them is when you multiply them. So I wrote these two multiplied together, right? Now, if you think about what happens when you multiply them, you get, well, you have to kind of FOIL it out, right? So if I go, let's see here. If I go to multiply this, if I go a times a, I get a squared. If I multiply a times b, I'm going to get ab. Oops, still on the highlighter. Go back. If I multiply this a and this b, I'm going to get negative ab. And finally, if I multiply the b and the b, I'm going to get b squared. Right? Except I just wrote that wrong because it should be minus b squared. Because it's a minus b and a plus b. Right? So you multiply that all out and you get what we wrote here. But you should notice that these middle terms are the same and they're just going to cancel. That's going to leave you with a squared minus b squared. And of course, this is something that you did know from the past, right? Like a squared minus b squared is a minus b, a plus b. Okay? Great, but how does that help us, right? How does that help us? Well, the way it helps us is because on the square root type, it does this. So what happens, here's another example. This isn't a limit, but this is going to be a square root thing. So what if I have square root x plus square root plus 2, and then square root x minus 2, right? What happens if I multiply those? Well, what's going to happen is the same thing that happened up here. Okay? We already know actually that the middle terms cancel, right? So the only terms that are left are a squared and b squared with a minus sign between them. So already when I see this conjugate pair multiplied together, I know my result should be something squared minus something squared. Does that make sense? Just based on this pattern, a squared minus b squared. Okay? Now what's the a and what's the b? Well, the a is just whatever you had right there, right? So what's a for us? Square root x, right? So you just put a square root x there. And then what's b? 2. So that's all you have to do. When you see square root x plus 2, square root x minus 2, it's just a squared b squared. What's it work out to? Well, the square root of x squared is going to be just x, and minus 2 squared is going to be 4. So there you go. That's what would happen to square root x plus 2, square root x minus 2. Okay? Now, the reason you care about this is because it lets you get rid of square roots. Square roots are bad when you're doing these problems because in limits, you can't really simplify stuff with square roots. It's hard, right? So that's why we're going to do it. So let's actually solve a problem now. This was all just preliminary. We're going to do the limit as x goes to, 5 of, I'm going to go, what am I going to go? Okay, let's go x minus 5 on top, and on bottom, let us go square root x minus square root 5. Oh, I don't like that. I'm changing it, sorry. I don't want one that has 2 square roots. That's why I'm changing it. Erase, erase, erase. So what do I want? How about 16? So x minus 16 on top, and on bottom, square root of x minus 4. That'll work, right? So let's say this is our problem and we're trying to evaluate it. So the first thing you try is you just try to plug in the 16 just because you want to make sure that you have to do something complicated, right? If it's just plug in the number and stop, you want to know that now. So put in the 16. You get 16 minus 16 over square root 16 minus 4. That's 0 over 0, right? So check that first. It's 0 over 0. You know that means we have more work to do. So then we move on and we do our work. So what we need to do is get the conjugate involved. So we need a conjugate. Okay, and here's how you do it. So this is where we're learning our work. Why is there an equal sign there? X minus 16, square root x minus 4. Okay. Here's how you do the conjugate. What you're going to do is you are going to look at, oh, nope, that's not going to work. Better color. What you're going to do is you're going to look at the square root part, right? Because this is a square root type of limit. You're going to see square root x minus 4, and you're going to write its conjugate right here, whatever the conjugate is. Now, remember, the only thing you do for a conjugate is you change the sign. So this minus just needs to be a plus. So you write square root x plus 4. That's your conjugate. Okay? Now, the thing is you can't just multiply by square root of x plus 4 in the denominator, because that's changing your limit. You're not trying to change your limit. You're trying to magically algebra away the 0 over 0. That's what we're trying to do. So if you multiply by the conjugate on the bottom, you also multiply by the conjugate on the top. Okay? So it's the conjugate, but it's the conjugate on the top and it's the conjugate on the bottom. Right? So square root x plus 4, square root x plus 4. Right? Needs to be the same thing here, top and bottom. Okay. Now, after you do that, then you're going to work out the algebra here. We're not looking at a limit yet. We're just trying to simplify the fraction. Okay? So what we've got, you can write it all in one limit here. X minus 16 parentheses square root x plus 4 over square root x minus 4 square root x plus 4. Right? Write it all in one fraction. That's just basic algebra. All right, now what? Well, look back up to our conjugates here. So the idea is when you multiply conjugates like this, it ends up just a squared b squared. So you just want to reproduce that down where we are, a squared minus b squared. So leave the top alone, right? Those aren't conjugates. Don't mess with them. Don't multiply them out. Don't do anything. In the denominator, that's where we need to multiply them out. So up here, leave alone. Here where the conjugates are, multiply out. Now I say multiply out, but I really mean just write a squared minus b squared. So remember, there's your a, there's your b. So a squared minus b squared. A squared, b squared. All right. Now from there, we just want to again leave the top alone. Don't mess with the part that doesn't have the conjugate in it. It's just wasted effort. Let's work out the denominator. So what's the square root of x squared? What's this? Just x. Okay. What's 4 squared? Just 16. Okay. So that's what our conjugate got us. Then what's next? What's next is you want to cancel terms. There should be something that cancels at this point. So specifically on this one, you should see an x minus 16 on the bottom and an x minus 16 on top. So those are going to cancel. So now what do you have? You have limit as x goes to 16, the top and the bottom, some stuff canceled. All you have left is square root x plus 4. Like that. Now, once your divide by 0 is gone, right? Like once the denominator is gone, right? Our divide by 0 is gone. And the divide by 0 was the problem. So now that the divide by 0 is gone, we can try to plug in x equals 16 again. Like we did way back at the beginning, right? Like we did up here. But we'll try again and we'll be successful. So try to plug in x equals 16 again. Oops, we're plugging in 16. So something we haven't talked about in notation yet, but when you plug in the x equals 16, you don't have to write the limit symbol anymore. Right? So notice at this step, I have no limit. But on the previous step, I have to write the limit. I wrote it on every line of work. Right? You need to as well. Every single line of work, you have to write the limit until you take the limit. So like we started with the limit, 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 limit. When we plug in x equals 16, no limit. That's the first time that you're allowed to not plug in the limit. Okay? Now what are we going to get for our result here? Well, square root of 16 is 4 plus 4, which is 8. That's the answer. Okay, that's a lot of work. Okay, I will admit that it is a lot of work, but that's how much work it takes. Okay, so here's what I'm going to do. I'm going to stop this video right here, and I'm just going to start a second video with the other two types in it. Just because this video is getting long. So see you then.